we booked this venue, there was no roadworks outside. So it would have been a beautiful, graceful, everyone would arrive on time. I know that just doesn't happen in the Middle East. People will still be coming along, so the doors will still be opening. But I want to thank you all for turning up and joining us for this, what is a launch, I suppose, of the SFE Hub in the Middle East again. It's been some time, and I'm representing Kuraray. We're sponsors of this event, and it's really great to see lots of you sitting down and waiting in anticipation for these great speakers that we've got lined up for you. What I'd like to do first is just bring to stage Benjamin Beer and also Mercedes. I'm practicing in my mind. I don't know. Mercedes. And we do have Andy York with us as well, but he's coming to the stage. That's fantastic. Okay, so these three people who you probably all know very, very well from the SFE, representatives of the SFE, they will have a few words to say, and then we'll continue with the speakers thereafter. So sit down and enjoy. Thank you very much.
So thank you, Alan. I'm very happy to announce the restart of the Society of Facade Engineering here in the Middle East. I have the pleasure of being the chairman of the regional hub of the SFE right now. This event took quite a while because I think since over 10 years, and there was no event. So I have to apologize that it took so long. We had COVID in between and some other reasons. So I'm very happy that we have this event restarting. I'm very happy that we have Kuraray as the main sponsor of this first event. I think tonight we have very interesting speakers. We have very technical topics. But before we start with the presentations, I would like to introduce the Society of Facade Engineering, who's actually organized this event together with Kuraray. I would like to introduce also the other committee members of the SFE in the Middle East, which is Mercedes and also Andy. I would like to hand over to Mercedes, giving a quick introduction about the SFE, about the goals of the SFE. That's okay? Yeah.
Thank you. So the SFE, for those who knows, it was the first accreditation, the first society created around the facade engineering role. It was created in 2004, and it was a joint initiative by the CIBSE, by SFE, and the Arup. It has been then hosted by the CIBSE, which is the Institute for Business Services, and it also run out a few societies like the Lighting Design and Social Engineering. And the courage of what we have is to recognize that role. For many of you, the first facade engineer is probably 30 years old as experience. So it was early in the 80s, 90s when it was created as a role. And since then has been expanded. Only in my company there are 300 people that calls the role of facade engineer. So it has a massive expanded, and the supply engineering is what we're trying to do is recognize that role.
Okay, can we move to the next slide? So who are we? What are our goals? So we want to promote professionalism in facade engineering. So we want to bring together facade experts or facade specialists or people working in the facade industry to promote knowledge, to bring us ahead as a facade professionals, as people ourselves. So we are planning a series of events. We're planning roughly every half a year, maybe a bit stretched out, about technical topics. And I think this is a bit of difference between other events, that our Society of Facade Engineering events are purely technical events. So all of the presentations are reviewed for technical content. And we want to push ahead new topics, important things that we feel are important for the facade industry here in the Middle East, especially. You can see our goals over here. It also can be found on the Society of Facade Engineering website. So you can take a scan, you can take your phone, you can scan this barcode. You're going to see more details. If you could go to the next slide, please. As I mentioned before, these are the committee members. So if you have any questions about the SFE, feel free to ask ourselves, Andy, Mercedes, myself. In the end, we depend on having members in the Middle East. So if you're not a member yet, feel free to join. We have different membership grades. We get newsletters. We're promoting the technical expertise in facade engineering. So feel free to go to the website and check it out. So today's event, I'm very happy that we could make it work. I'm very happy about Kuraray, and I'm looking forward to the presentations. Thank you. So the first presentation will be by Kuraray. We then have other presentations. We're going to have about 4 presentations tonight. After the presentations, we're going to have some finger food out there. I think everybody of you might be hungry after this event. So there's going to be drinks and finger food afterwards. And I would hand over to Allan from Kuraray.
We go back. We can work it. Mine is.
It's
Right. So, welcome to the SFE event here at the beautiful hotel, by the way. Gorgeous hotel for those of you who haven't been here before. I was asked to go through some risks and reasons associated with the failure of delamination. So I hope you'll find this presentation useful. I've been in the industry for 24 years, specifying specialist products for the construction industry. And I have actually studied the SFE Society of Façade Engineers Masters, which we did for the CWCT. And I'm responsible for the delivery and specification of Kuraray's high performance products within Northern Europe. I've worked in the Middle East as well over the last few years. But this particular presentation has been brought to you by Kuraray, and it underlines their commitment towards serving the ever-changing demands of the global glass industry. Today I wanted to go through, I don't know why this isn't working, sorry.
next slide.
You can go back one, please. And again. Yes. Okay, thank you. So I'll just go like that and then we'll change the slide. Thank you. It's not very so today I want to go through the following topics. A quick introduction to the overview of components that constitute laminated glass and how they can contribute to poor lamination, resulting in delamination, or the effect of the aesthetic of laminated glass. Then we'll end with a serious topic that's quite prevalent here in the Middle East. Okay, this will be fun, isn't it? So Kuraray's advanced interlayer business is a leading global specialist in the development, manufacture and supply of PVB and ionoplast interlayers for the laminated safety glass applications for architectural, automotive and marine industries. And this is all provided by a truly global business full of diversity, with more than 900 employees, more than operating in 20 countries, with 7 manufacturing plants, multiple R&D, technical service locations throughout the globe. And it provides a local service to support our valued customers and project stakeholders. And this is possibly but this is all possible with a multiplicity of specialist interlayers manufactured by the division of Kuraray. And it provides solutions in the areas of safety, decorative, acoustic control, structural and security, and other specialist applications, automotive, transportation, and of course sustainability, which is really high on the agenda of much construction at the moment. So why is it that sometimes delamination occurs? Over the last 50 years, the use of laminated safety glass in architecture has been widely accepted to provide safety, additional performance qualities such as load bearing, glass, ballistics, and forced entry protection. But now with a greater understanding of the environment of the enclosed building skin, We look for additional attributes for laminated safety glass like solar and energy regulation, UV penetration control, and acoustic attenuation. And the demand of laminated glass has grown exponentially. And so too is our understanding of why sometimes it can fail. The laminated safety glass is when two or more plies of glass are bonded together with an interlayer. The most commonly used interlayer is PVB, polyvinyl butyrol. And then this is referred to as laminated safety glass. But we also manufacture sentry glass or an Iona glass, which is very commonly used in the UAE. And due to its edge stability, structural qualities, and performance in the hotter climate. But the primary purpose of the interlayer is to hold the broken particles of glass should the glass break. It holds it in situ and prevents it from from falling down and causing injury or fatalities. There are many elements that can affect the delivery of a stable quality panel of laminated safety glass. And I know Pascoal will go through some of these in a bit more detail later, but however, what I want to do is look in particular at the delamination causes. And these are caused by influence associated with the interlayer or the glass. And as you can see in the image, not all glass is the same. Some is rough, some is smooth. Some interlayers are not the same. Some have higher adhesion strengths than others. Treatments, cleaning, processing, and production can all influence the final outcome. The chemical interaction that promotes the bond between the interlayer and glass cannot accept any impurities. The removal of all washing, rinsing residues, scale residues, releasing agents, bicarbonate, and others, corrosion residues, cutting oils, grease, detergent residues from cleaning agents, and also glass chips during processing. Next slide, please. Proper glass cleaning requires quality water. Only demineralized water with a conductivity of less than 20 microsiemens is effective to ensure a strong adhesion bond of the polymer and the glass. And as important is the storage of the interlayer. Moisture content of the material can adversely affect the adhesion qualities. Rolls are supplied in a protective film made of aluminium and aluminium coated polyethylene. And that prevents moisture ingress whilst the roll is being stored. And after use, it really should be resealed. Or if the roll is opened, it should be stored in a humidity controlled environment. Sentry glass, however, is slightly different. It's recommended that the interlayer not be used if the moisture is above 0.2%, and when measured by the Carl-Fisher titration. So once this level is exceeded, the moisture content, it cannot be reversed, unlike PVB, and storage needs to be below 20% relative humidity, ideally resealed. So unlike sentry glass, PVB can be dehumidified to 0.3% moisture content, but if it once it's allowed to reacclimatize itself in the correct environment. Rolls with a PE interleave, which is very common, and can be sealed back and stored at 30 degrees Celsius for a long term. In a humidity controlled environment, it can last a lot longer, but the refrigeration needs to be around about 18 degrees Celsius. And you're looking at a shelf life of around about 4 years. So we know that works. So what is the cause? So now let's look at some of those causes of delamination. As a manufacturer, we run extensive tests to ensure the suitability and the production quality of the material. But from a quality perspective, the ISO 12543 Part 4 provides test methods for durability, and it mimics the excessive conditions expected when the material is in an installed state. Now, the three main objectives is to look at the aesthetics and measures bubbles, cloudiness, and ultimate delamination. And this is a similar methodology, sorry, next slide, used for sealing compatibility, which I'll go through later. And methods of testing, as you can see, temperature, humidity, and solar radiation. Right, next slide again, please. Sorry, I forgot to give you the pointer tonight. No, next slide. And again. And again. Yeah, so these are the test methods for the usability, looking at the three different options, which is temperature, humidity, and solar radiation. Next slide, please. Yeah, we're getting there. Overall bow may also vary dependent on glass diameter and thickness, size, aspect, and ratio, and other factors like roller weight caused by the glass moving over a roller at high temperatures when the glass is being fully tempered. This will give a slight waviness to the glass, and it can be very much affected by the thickness of the glass, but also the pitch of the rollers. This is what is commonly known as roller wave. Now, standards in BSEN 12.50 Part 1 for toughened soda lime silicate safety glass state accepts limits of overall bow and roller wave tolerances between 0.2 and 0.5 millimeters as an acceptable standard, depending on the glass type and thickness, etc. But most processors will in fact produce lower than that. When dealing with interlayers with a gauge of 0.76 millimeters, for instance, with a tolerance of 0.5 millimeters, there is a high risk that all that void will not be filled. Click again. There you go. Not be filled, and especially during the processing where you're squeezing the plies of glass together under heat to extract as much of the air as possible, it will apply pressure, and then it'll be autoclaved. But should this occur, then over time, when the material is installed with thermal movement of expansion and contraction, it can open up and prise open the glass and reveal the laminated glass, and an air pocket or failure can occur as a result of that. Next slide, please. So these images show the results and effects of an open edge that has been subject to accelerated weather testing or salt spray testing, appropriate to those installations around the coastline, high humidity conditions, similar to the property plan. ASTM B117 is a 3,000-hour test at temperature with a relative humidity of 100% using a saline solution. The top two samples show no effect, but the bottom two samples you can see show signs of moisture ingress due to the hygroscopic properties of PVB. It becomes milky and cloudy around the perimeter of the panel, and over time it will affect the transparency and the visual effect of the laminated glass. Worst case scenario, it will delaminate over time. Next slide, please. Before assembly, ensure that the glass is dry. The sentry glass must utilize the following constructions. Laminated safety glass directly to the tin side. There's two sides of glass, an air side and a tin side. When it's floating over a tin bath, that's when you get the nice smooth float glass, as it's commonly known as. And the side that's on the tin is known as the tin side, and the side that's not on the tin is called the air side. Now, when you're laminating sentry glass, you should laminate with tin side, sentry glass, tin side. So you've got the two air sides on the outside. But what happens if you have multiple plies, especially when we look at the bullet resistant glass and multiple, for structural glazing, you may have 2 or 3 or maybe even 4 plies of glass laminated with sentry glass. What do you do then? Use an adhesion promoter. So you apply an adhesion promoter to the air side, and that allows the sentry glass then to bond with that air side of the glass. However, it could be applied inappropriately. It could be too thick, or maybe the adhesion promoter is out of date. So if you apply excessive amounts of this adhesion promoter, then this too could cause issues at another stage of installation. Now, the cooling rate of an autoclave, or the pressure cooker that the laminated glass is put into to disperse the air during the processing, needs to be rapidly cooled, bit differently to a PVB. And the cooling of century glass to at a rate of 2.2 degrees Celsius per minute will help to reduce that risk of haze, which can often be associated with century glass also. However, if you were to cool it down too fast, then you have a risk of producing iridescence. So it's a very, it's almost like black magic. These glass processes, they have a lot to deal with: cleaning the glass, laminating, making sure that everything is correct. But it's not just the glass or the glass processing that could cause the defects. Look at moisture. We're looking at frames now. If gaskets or seals break down, it can leave the interlayer fully submerged in water. Get a lot of moisture content in the air, condensates on the cool glass, drips into the frame, and then the interlayer is in a pool of water. Because of PVB is hygroscopic, it will absorb the moisture and could cause that milky hue that we saw on the spot spray test earlier. Worst case scenario, and it happens quite often in the Middle East, is that the materials will be ready, they'll be shipped to site, but then they'll stay in storage on site many, many weeks to come before they're actually installed. All those open edges over time were drawing the moisture, looks fine. Then they'll be installed, trapping all that moisture. And as you can see on the image there, this could seal in the moisture and then cause a risk of delamination at a later stage. Next slide. Oh, sorry, for tasking. There you go. So the image there on the right-hand side. Next slide again. Now, ASTM 61087 looks at sealing compatibility. I know we have it down here. And it's a test method that checks defects. It's also partially covered under the EN ISO 12543 Part 4, but it doesn't necessarily look at the discoloration as well. And the compatibility of two or more materials consist in their capacity to coexist in a juxtaposition for a long period of time, which manifests signs of detachment or delamination, discoloration, or alterations that may occur during chemical interactions. That's the terminology that's used for the test method. Next slide, please. So the test method for the checking of sealing compatibility is similar to the accelerated test that I showed you earlier. To check the quality of laminated interlayer glass. But this has also has some similarities to a performance monitoring testing regime that we have for century glass samples. They're sent to our lab by a laminator to receive an approved century glass laminator status, where the samples are subject to a bake test where temperatures are ramped up to 150 degrees, not the 100 degrees that you see there. Pummel test, lesion test, and we also test for moisture. But the sealants run through the similar tests that I showed you earlier for the suitability. And the compatibility test gives us data recording visible defects, which could be edge bubbles, a chain of bubbles, or channels and discoloration. Next slide, please. See the edge bubbles and discoloration. So all this information, all this data is logged and is available to you later. Next slide, please. Now, the depth of delamination, the degree of adhesion loss between the panels, or the visual milky effect that we saw in the salt spray test, are also available and also observed. Next slide, please. Now, these issues are not only local to the perimeter of the unit. You can see around the perimeter of a point fixed panel that this could be caused by the incompatibility of the adhesion or possibly poor lamination. Next slide, please. Now, much research has been carried out by the main suppliers of sealants and adhesives, and we have compiled an extensive list of compatibility test data to help ensure correct sealant is chosen for the appropriate role. And this is available on request, and it's constantly being updated. So if you have a copy of this, make sure that you're requesting it on a regular basis to ensure compatibility. So there is no single, next slide please. There is no single standard for optical performance Limitations only measure the glass surface, scratches, inclusions, optical performance like light transmission, but not the clarity. Next slide, please. Kuraray Interlayer boasts the lowest readings on the yellow index, which is why they're the most popular for architectural industry. Especially with the increased use of low iron glass, clarity is key, and the ultra clear and central glass products are the best performance in this field. Or when using tints with a PVB, you wouldn't want the yellowish effect to tone the finished result, would you? Next slide, please. There is no standard for the optical clarity of laminated glass, but much is known about the index of refraction that measures a ray of light as it travels from one medium to another. As it begins to travel through a material, the interaction between electrons and photons reduces the speed of light, and as the density of electrons increase, the velocity of light becomes slower. And that's why light moves at the highest possible speed in a vacuum. Now, the light's transmission angle can be calculated using Snell's law, and the discrepancy between the light transmission and the incident angle becomes bigger as the index of refraction becomes larger. Now, a change in the index of refraction due to the change of the wavelength is known as the chromatic dispersion. Now, the more layers in the construction, or the greater the angle of the incidence, it can increase this factor, causing ghost images. And this is why a mono interlayer, a mono acoustic interlayer, can reduce those number of layers and reduce this optical effect. But also the clarity and the coupling effects of an interlayer can add additional benefits to affect the chromatic dispersion. Next slide, please. But now I'll finish with the beware. Cost of ownership is heavily influenced by the right product ultimately being fit for purpose. However, that product that is fit for purpose may also offer additional attributes and added benefits. These added benefits may improve structural, optical, and thermal performance, sound reduction, solar control, ease of maintenance, etc. Next slide, please. And here are some of the other factors that influence the cost of ownership. In my short time within the industry, I have witnessed some failings that have resulted in very costly replacements. Replacements that were needless and often associated with specifications that were not fit for purpose, or later became generic during the tendering process, therefore opening that door to similar or approved or value engineering, without fully understanding the reason behind the original specification. Now, we all know not all products are the same or have the same qualities, and they perform differently in different situations. As an example, open edge retention, delamination, or due to other issues, due to sealant, the wrong sealant, these can become apparent post-installation. The correct interlayer will help prevent the risk of moisture ingress along that open edge. Incompatible sealants can cause delamination issues, and this can be avoided if correct guidance is followed. Defects due to too much stress causing ice flower deformations in acoustic laminated glass can be avoided with the use of monolayer products. Be sure to use the correct interlayer for balustrades and overhead glazing. Attention is required on the expected loads and the anticipated ambient temperatures of the installation. Guidance notes from CWCT are very useful for this information. Just be mindful of the use of the term PVB, acoustic PVB, structural interlayer, SGP may not always deliver what you require for that project. There may be the risk that the use of the term SGP in your specification may open the door to unqualified Chinese copycat fake century glass imports being installed on your project. Registered names need to be used in full: century glass, SG, century glass extra, SGX. By influencing the specification with the correct product names or including technical data specific to the correct interlayer, we can help ensure the right product is installed. We have been manufacturing interlayers for the architectural industry for over 50 years. with the knowledge, experience, and product development to support this. And the biggest compliment for any manufacturer is imitation. And as a result, we are constantly aware of copycat products that infringe our copyrights and patents. But despite this ongoing responsibility, it's you, the specifier, the client, or the customer that ultimately carries the risk associated with the use of these inferior products and can burden those life cycle costs that far outweigh the initial cost saving that could be achieved by swapping to a less qualified or quality product. Sorry, next slide, please. I got carried away. It's very emotional part of that. Go on, carry on, please. Next slide. Okay, we've got a bulletin on this, which is available on the table with regards to the famous century glass. Middle East is being swamped with it. Do be aware of it. It's a big risk, a really big risk. Next one, please. Okay, I've also got a card with a QR code available. There's a really great app you can download on your phone. Gives you access to our website. Loads of free to use apps to work out certain values, gains, weight, and everything else like that. This presentation has been brought to you by Kuraray, and it does underline their commitment to the ever-changing demands of the global glass industry and through innovation and leadership. Thank you very much for your time. Now I'd like to welcome to the stage Mr. Pascoal.
Good evening to all. Thanks to the Society of Facade Engineers and Kuraray for hosting this event. Thanks for the introduction, Allan. You have proposed glass processors as Harry Potter as black magicians. So what I'm going to talk about is about some black magic. So we can learn something today and try to practice it at home. So laminated glass, as we look at it, is a perfect blend of beauty, strength, and safety. Bear with me if I'm a little bit loud, because we work in a factory, so we have always this habit of speaking loud. But it delivers what we need to say to you. It's a perfect blend of beauty, strength, and safety. I didn't add the durability part of it because we are going to look at what it means to have laminated glass on your building. Because one of the key important thing is durability. And so we are going to look at the process control, that's the black magic part of it. Then we are going to touch on a little bit of blast resistance and bullet resistant glazing. So my name is Pascoal D'Silva. I have been in the industry, glass and glazing industry, for nearly 25 years. Out of the 25 years, 20 years, I've been working with Gulf Glass Industries. Some of them know Gulf Glass Industries. It's a 31 years old company. The first company to laminate glass in the UAE and the Middle East. So we're the first laminators. So what we're sharing here is all about our 20 years of experience in laminating glass. Apart from that, we were the first ones to install the Sentry glass, laminated exposed edge glass on a building on the Sheikh Zayed Road, and it was in 2009. So by now it has passed its warranty, but it is still looking good. It's a building by the name of Maze Tower. If you ever get a chance, you can have a look at those laminated glasses, exposed edge, perfect beauty. Next slide, please. Still getting. So laminated glass, there are many interlayers, the types of interlayers that Kuraray, Allan has touched. I would just expound on that. There's something which is EVA. We have polycarbonate and PU, and we have cast in place, which is known as resin. So these are the type of interlayers that go into laminated safety glass. It is not making a laminated glass. It's not an easy thing. It's a very, very sophisticated control process. And that's why we need to look at the process control. You can see the two main ingredients or the two main criteria are glass and the interlayer. The next slide, please. So what are the critical factors that affect the laminate quality? Is first, material. Second is the process. Third is the installation and maintenance, which Allan has touched on a little bit. But I would go on to next slide. Okay. Cheap can be expensive. And this is what is happening, and this is what we find mostly. Laminated glass, until 10 years back, everybody specified, architects were saying this 5 years laminated glass warranty. Now we have specifications which are asking for 10 years, extended to 15 years, extended to 20 years. When we go to PVP manufacturers and they say, guys, this is your problem. You are the black magician, you deal with it. And so the specifications and the life expectancy of a laminated glass is 25 years. So how do you give a product in this market that is going to reach such sort of warranties or life cycle? So that's the critical thing. Until 10 years back, we had only five PVB manufacturers. Today we have 50. And none of them have accelerated test or weathering test done as what our dear friend Allan showed us of accelerated weather test or the weathability test. So it is something that cheap can be expensive, and especially if you have a building where you have laminated glass. Next slide, please. Okay. The critical thing is, the critical factor we spoke about is interlayer. The second thing is glass, and that is the main ingredient. If you do not cut your glass properly, and that is why we are the processors, you need to be very careful of how you process the glass. So if the quality of the glass edge is not perfect, it will affect your heat treatment quality. And the next slide, please. Heat treatment affects the flatness of your glass. That means roller wave, edge lift, and overall roll. Next slide, please. So it all begins with glass. Lamination begins with glass, not interlayer. It begins with getting your glass right. So the European standards, which Allan referred to, is 121501863 BSEN, ASTM 1048. Does not have much of a thing, but the most stringent one is the EN standard, which is 12150. And 1863. But those, if you look at it, those European standards for toughened glass or heat strengthened glass are not good enough for lamination. And specifications are still continuing with European standard, and we say, oh, we follow the European standard. What is recommended flatness for laminated glass, heat treated flat glass is something like this. Roller wave should be less than or equal to 0.08 compared to the 0.3 mm, which is the standard. Edge lift, 0.15 mm compared to what you have in the standard, which is 0.25. Local bow, 50% down, less than 1.5 mm per meter compared to 3 mm. So the question is, I have 10,000, 20,000 square meters of glass laminated. How do you control it? And next slide, please. Technology has advanced. You can measure each and every piece of glass that comes out, especially for laminated glass, and make sure that your values are in those range. So what you see there is PVL, PVM, and PVT. That is the peak to valley of the leading edge, which is the edge lift, 0.05, 0.03 mm. PVM is the roller wave, which goes to maximum 0.05 and the trailing edge. Now, these are critical flatness that can give you a better quality laminate. Heat treatment quality is critical to the lamination quality. Next slide, please. Just a process. This is the lamination process. Looks easy: loading, cleaning, drying, positioning, roll storage. It looks like a laundry thing, but it is not. De-airing process, unloading, and then autoclave process. Next. we have spoken about this. It's the addition, at least for PVB, is the hydro oxides, which are from the PVB, which is bonding to the silicon, and that's the perfect laminate that you would have. But unfortunately, there is no laminator who can give you this sort of a perfect laminate. Next slide, we will look at it. Why we are saying that air side and inside. The moment you have on your glass alkaline or earth alkaline metal ions, it will create an interaction. It will create a problem for your addition. And so this cannot be avoided. In the Middle East today, everyone wants a glass which is outside laminated glass, coated laminated glass. You cannot have air to air side on a PVB, on a laminated coated glass, because coated glass has one side which has coating and it is the air side. So the only side balance for you to laminate is the tin side. And so there comes a challenge for PVB manufacturers when you're putting glass on the external facade, is to use high addition PVBs. And nobody talks about it because it's not there. So anybody can use a low addition PVB and then you get after 5 years delaminations. So this is critical because it is chemistry, it is what it is. For century glass, you cannot laminate on the air side. So you have addition promoters. So those work. Next slide, please. We spoke about washing. So the water that we drink is having a conductivity of nearly 670 microsiemens. The water that we use in washing the laminate is only 16 to 20 microsiemens. So you need to be careful is that who is processing your glass, how it is being processed. So the conductivity of water also affects your lamination. It will have variability in addition, and that will cause delaminations later on and bubbles. Next, I need to have some water. Influence of water in addition. A single drop of water on the PVB or on the glass is a disaster for your lamination. So the glass that comes out has to be perfectly washed, dry, and clean, just like how my wife does it. So you need to bond it perfectly and no water on it. So that's the thing. The next one. Room conditions. You look at this guy, they enjoy working here for the next 3 months because the temperature inside there is less than 25 degrees. Relative humidity is 18 to 25%. So that sort of control condition is very critical because once you supply the laminate to your project, it looks perfect. The problem starts after 3 years, 4 years, 5 years. And if you have asked for 10 years warranty, sometimes either the processor is missing or the PVB manufacturer is closed down. That's not the case with Kuraray. They said 50 years. So we have been doing lamination for them for 25 years. So we can stand and confidently say that we do not have such issues. There are problems. We have learned from our experiences. But this is what makes us good laminators. Next. De-airing process is very important. You need to remove all the air. You have 2 glasses and the layer, and then you press it and remove all the air. A little bit of a more amount of air that remains in the laminate will cause bubbles on the side. So each and every single adjustment that is done on this de-airing will affect the quality of your final laminate. So there are line speed, oven temperature, pressure, heaters. The heaters are now mostly convection heaters, so they are more effective. Next slide, please. Vacuum bag. We are talking about bullet resistant glass, curved glass. The only way you can do that is through using either vacuum bags or silicone bags. The productivity is low, but the efficiency of getting a good laminate out of a de-airing coming from such process, vacuum bag process, is very good. But it's difficult to process glasses as laminate flat glasses through the vacuum bag. There are a lot of demands nowadays where you have metal interlayers in the lamination. So this is the process that can give you optimum quality. Next. This might sound simple, loading the glasses, but this is the after you do everything and you get this wrong, you can have a sunburst delamination on the edges, just like many of us have seen half moon shape. That's because many of the people don't understand that as you stack the glasses into the autoclave, there is chances of pressure points that can come on the glass. So in the middle, what you see is always try to keep the laminate freestanding, not on as having pressure points. And the last one is the autoclave, which Allan has already spoken about. Autoclave conditions and cycles are very important. Otherwise, you will end up having haze or inadequate addition. Next, please. So pummel test, just a picture of how pummel test is done to check whether it is high addition, medium addition, and low addition. So it's done at minus 18 degrees centigrade using a freezer. That's for checking the addition. The second one, next slide. This is where the temperature test is done. So basically you're raising, keeping the glass at 100 degrees centigrade for 16 hours, and then incrementally increasing it 1 hour, up to 130. But after 130, you can go it up to 180, 190. Temperature resistant test is very critical, considering that we are in a country where the glass temperatures can easily go up to 100 degrees centigrade. And if it is a spandrel glass, that can be much more higher. And so using laminated glass in spandrels, you need to, as most of them might be well engineered or well known on this fact that the temperature in the laminated glasses can go very high. Next. This is easy test. Just summertime is down, take a bucket of water, it is already 100 degrees, put your laminate and check it out. So that's the boil test. You just put it in the hot water for 2 hours. If you see bubbles, make your cling. Next. The important part is security glazing, and Kuraray and Society of Facade Engineers wanted me to touch on this. Why security glazing is so important is because architects for the last few 30, 40 years want transparency. They want glass everywhere, minimal systems. And there's a high demand of transparency and getting more in the light and keeping the heat outside. But we have to be a little bit cautious when we are doing such designs or where the buildings are located, because security glazing, the focus is to reduce the risk of injury and material damage. So it's about people and it's about property, and both is important. So next slide, please. So we are not going to touch on the anti-bandit or the forced entry. That's not the topic that I'm going to touch. I'm going to touch on explosions, man-made threats. That's very important. Is all of these are man-made threats. Although we want a safety around us, it's not possible to always have people who would be safe enough, or they have other motives. Apart from that, there are chances that hazardous materials are lying somewhere. And there is a possibility that due to the negligence of some people, there could be explosions. The next slide. Window glass and the facade element is the weakest element in a facade, whether probably many of them will agree with it, some may not agree. But what we have seen this and experienced is the window and the glass facade element is the weakest element on the risk of blast threats is when you have an explosion, there's always the risk of glass flying off, debris falls, damage to the building, and depend upon the explode charge, and most of it we are always talking about glass, but what about the anchoring of the glass into the framing system, which is very critical, and the frame to the structure. Next slide, please. Can you play that? So that is an explosion on port which happened in August 2020. 2,750 tons of ammonium nitrate. That was the effect of 2,750 tons of ammonium nitrate, which was stored. And when it did blast, and it was not probably due to an accident, human mistake, or negligence. It was not a terrorist attack, and I'm not touching terrorist attack today. I'm talking about explosions that can happen due to negligence and accidents. The 2,750 tons of kgs of explosion that was there was equivalent to nearly 500 tons of TNT that can explode. And the effects were seen approximately 3 to 5 kilometers away from the place where the explosion happened. Next one. This is the building, which is the electricity department headquarters of Lebanon. Before the explosion, everything is with the facade. I have just checked my sources. They said it was double glazed, monolithic tempered glass, which was there. Next slide, please. And this is the, just 2 days after that, there's no glass there. Not one, which is strange enough. You could see small particles of tempered glass stuck into the frame. Everything was probably sucked out or pushed in. And you can see the property damage that is done. Next slide. That was 3 kilometers away. This is another building, no facade. The glazing or the glass is completely off. The aluminum structure is still there. Can you press? Yeah, that's St. George Church, which is 2 kilometers away from the place. They did use laminated glass, but the laminated glass along with the frame is completely inside. It has been pushed inside because of the impulse force. Next slide, please. Laminated glasses. This is 3 to 4 kilometers away. What you are seeing there is hanging balustrades. The balustrades have broken, and I'm not sure whether it was PVB or EVA. It couldn't have been SGP, but those have, due to the blast, they are broken and they are hanging like blankets. The worry is it can fall anytime, and when it falls, it will fall like a blanket and even kill a person. Next slide. That is the building, which is approximately 4 kilometers away from the port. And you could see laminated glass there. It has taken the impact. It has, even though the structure is bent a little bit, but it still has done its part of glazing. Next one. Not far away, if we say explosions won't happen in UAE, in Kharij times in May 23rd, 2022, we had an explosion in Abu Dhabi. 2 dead, 120 injured. Nearly 6 residential buildings have been affected by the blast. And you can actually see tempered glasses particles down there. Next one. And this was in the newspaper. Windows have been shattered in the buildings and shops of the next street. It was a major fire, and in fact, I have not seen anything like this in the past 10 years here. So explosions, accidents can happen anywhere. Are we ready for it? Next. Can you press? This is an explosion test, which is done, arena test, and you can actually see the positive phase. There it comes at slow motion, and the glass breaks. That's the positive phase. It's for a few milliseconds, and then you have the suction, which is the negative phase, which goes on for much more longer time. That's when the whole glazing is sucked out. It was done by Saint Gobain Glass Solutions in UK. Next. So those are the characteristics. You have an overpressure in kilopascals. The one which happened in Lebanon was 80 kilopascals. We designed buildings to 2.5 kilopascals or 2.8 kilopascals wind loads, if I'm not mistaken, most of the time. But 80 kilopascals is something that glass cannot really handle unless it is designed for that. The impulse is basically the measure of energy from an explosion onto the building. So these are the characteristics of positive phase. The next one. The negative phase is that one where it is pulling or sucking that out. The pressure is not high, but the time duration is quite long in the negative phase. Next. So here you have the key thing is overpressure, impulse, and the other thing which is very important is the proximity of where the blast is happening. That is the reason you have roadblocks and barricades and stuff like that, securities, depending upon the impact that can have on people's properties. So if you have a device of 100 kg TNT, your overpressure at 50 meters standoff distance is 28 kilopascals. The impulse is 255 kilopascals. So this is a table that can give you an idea of the standoff distance is very important. So when you design buildings close to something that is a security zone, you need to consider the standoff distance. Next slide, please. Rule of thumb, the bigger the bomb, the higher the overpressure, the longer the duration. The closer you are, the worse the blast pressure you will feel. Greater standoff needed for more explosive devices. Those are the rule of thumb. Next. Codes. Next. So these are all the codes that are there. We have basically spoke EN standards. There's shock tube standard and also range or arena test, but they are different. For glass, it is EN 13541, which is only for glass glazing. But as for windows, shutters, and the other part, you have shock tube and arena test. Next slide. Can you press it? This is the volume. Wait for it. Okay. That's a shock tube that's in US. The pressure builds there, that's a thermite charge. And this is the diaphragm that flows out at the end of the shock tube. So that's the testing that is done so that you don't have to do it on the arena because it's much costly. Shock tube testings are much more economical. Next slide. This is again classifications ER1, ER2, ER3 based on the standard, giving you idea of the blast wave, the impulse, and the duration of the effect. Next, please. Next. Can you play that? Yeah. So this is the right type of interlayer. You can see the impact that is taken by the interlayer, and the pressure is now blown off. The next. Sorry, go back. Play that. Yeah. The other. Okay, the other one was just tearing off. This is the arena testing based on ISO 16933. So you can even do arena testing with 70 kilopascals. You have hand carried and vehicle bombs. So you can actually do that in arena testing. Next. This is the American standard where you have the ISC security glazing and GSA, which gives you much more different criteria for accepting, is that when the blast happens, how far will the glass fragments go? That is a category that is additionally put in the American standard. Next. Finally, another 2 slides to go. Elastic glazing. Next, please. Why it is so important is there's a high demand now for people, high-profile individuals and people who need bullet-resistant glazing, and it is just going up and up. At least in the Middle East, a lot of people are asking for ballistic glazing. The type of ammunition, the injury from the bullet and the injury from the glass pulse is one of the criteria. Next, please. So these are BR1, BR2, 7 categories. There's one sample, which is BR7, which we have kept there, which is the 7.62 into 51 armor piercing. You can have BR5, which is AK-47, BR6, M16. Next slide, please. You have even shotguns in this classification. Next. And the classification has no spall and spall. So it is, you can have both. Non-spall is for people probably in the banks or people who are very close to the glass, and there is a possibility that the spall or the shatter of the glass can impact or hit you, and you could have injuries. Next. This is the American standard, National Institute of Justice, level 1, level 2, level 3, level 4. And then you have Underwriters Laboratory UL 752, which you have the range of rifles, ammunitions, which have to be used. Next. This is the equipment that is used in the laboratory. They do not use weapons, so they do not carry AK-57 or the M16 all the time with them. They have something which is like this, so they put the right caliber and they shoot it. Next one. Next. Can you play? So this is BR6 bullet-resistant glass, which is anti-spall. And this is the last slide. So the short one, you can actually see the spall just flying off. The bullet is not penetrated from the other side. And when you have the other one, you actually see the bullet hitting and the spall being captured by your special film. Sure, done. Next slide. I know within this 25-30 minutes, Andy told me, Pascal, how are you going to finish this off? I have completed it. You still have a chance if anybody wants to basically come and have a day to explain the standards and more in detail. We have something known as a day of glass at GGI. So you are more than welcome to visit us. We are not trying to sell you. We are trying to just share our experiences and have a one-to-one communication with you. Next. Thank you very much.
So many thanks, Pascal. It was really appreciated. So both of the presentations, I was really amazed about the in-depth technical content. I hope we're going to come to the last presentation right now. So this last presentation is going to be about some research topics that are currently ongoing. So I'm going to have the pleasure to start with a few slides from my side, and I'm going to hand over to one of our online presenters, which is Professor Dr. Lucio Blandini from the University of Stuttgart in Germany. So as I mentioned, I'm going to start with a few slides from my side, then I'm going to hand over to this online Teams presentation. Hope everything works out. You can see Lucio already on this online. So I would give it a start. So we'll go to the next slide. Maybe go to the next one already. Now, why are we doing all of these interlayers? So why do we laminate it? Why do we laminate the glass? It's mainly because of safety. Safety then comes to human beings. So we're doing all of this because of us as human beings. Why do we doing facades? Why do we do glazing at all? Why do we glass? Because it's for us as human beings predominantly. So glass transfers light into our buildings. So in the end, we're doing all of this predominantly for us as a human being. And there's this new thing about calling human-centric design. So we're trying to refocus all of our design, all of what we do, also the research, that we refocus on the human being itself. Of course, we still consider sustainability, but this kind of focus in mind, we want to talk about interlayers. And what's quite interesting, because I was talking about human beings, what about plants? Now there are specialist interlayers also by Kuraray that transmits also the UV light. You know, whatever we do with our glass, either with the coatings on the glass, like solar control coatings or interlayers, we're filtering out a certain spectrum of the wavelength, yeah, from the solar spectrum that comes from the sun. Now, for example, Kuraray has this product, which is especially for greenhouses. It's got the Century Glass Natural UV, so it's an interlayer, because usually PVB interlayers, they block the vast majority of UV light. Now, this UV light is needed by the plants, or there's a lot of discussion with botanical specialists, is it the plants or the small animals in the plants? Nevertheless, we know what plants need. This also brings us, if we have these artificial greenhouses or the so-called vertical indoor farms, there was a lot of research being carried out. What kind of light spectrum do the plants need? Yeah, and usually you can see in this vertical farms is kind of pinkish spectrum. So of course, a major component is the blue light and the UV light, which is then transmitted by the interlayer. But if we look into artificial lighting, yeah, there was a lot of research being carried out. What kind of light do the plants need? And we have 3 peaks in the blue, red spectrum, and so on. And this is what these vertical farms are then using. If we go to the next slide. And so there's a lot of research. What kind of spectrum do the plants need? You can see these kind of 3 peaks over there, and we know exactly what is the wavelength. Now, in principle, talking about solar spectrum, what our human eye can see is around from 380 nanometer wavelengths to about 780 nanometer wavelengths. This is so-called visible spectrum. And this is what all of our coatings on the glass, and also, of course, the interlayers are optimized, that we have a high transmittance to the glass in the spectrum, because this is for the human being. Everything else, ideally, is either reflected or absorbed, because this is solar energy, and we want to keep it out to reduce our cooling loads. If we go to the next slide. Now, the big question is, yeah, so this is now plants, and you can nicely see that on the left-hand side, everything is kind of greenish. Yeah, so this is the light that is switched on for human beings. Now, on the right-hand side, you can see a little bit of this purple light, and this is the actual light what the plants need. Yeah, so these vertical farms have 2 light modes, one for human beings to clean and whatever they need to do maintenance, and then the actual light, which is the kind of purple spectrum, which is for the plants. We go to the next slide now. You might ask, why is this guy there talking about plants and we're talking about laminated glass and facades? Now, the key question is, do we know precisely what we need as a human being? Yeah. And I'm currently running a research project with Guardian Glass about a more human-centric design of solar control coatings. Right now, our coatings are purely optimized to reduce the solar heat gain while still transmitting a maximum of visible spectrum. Now, why do we need light, and why do we need a certain quality of light? Now, these are actually submarine soldiers shortly after World War, or during World War II. And already quite early, it was figured out that human beings need natural daylight. Artificial light is not sufficient. If we would stay in this room for a whole day, we're getting very tired. And so, oh, when is this over? So we already know that we need certain natural daylight. And this natural daylight was also found back in the day. So these soldiers have been in the submarine for several days and days or months, and they were getting sick. So already back in the days, the soldiers were taken out into sunlight, or kind of what they believed would simulate sunlight. We go to the next slide. We know the so-called sick building syndrome, like 1970s, people working in offices only being exposed to artificial light. We know this is getting people more or less depressive. Go to the next slide. And this is a bit of the research that we're currently focusing on. So what is the quality of light that we as a human being need? Or do we need light? This is a very nice map on the left-hand side. This is the percentage of people with depression and anxiety. This is the percentage of medication of the people, yeah, against depression. And on the right-hand side, we see the average daily sunlight, yeah. And what we can nicely see is that these states in the United States with a high degree of natural sunlight, like Texas, California, and so on. So these are the kind of states with the lowest percentage of prescription against depression, only about 6%. So there's a very clear correlation between exposure to sunlight and people getting depressed. Go to the next slide. We as a human being, we got an indoor species, yeah? We're no longer outdoor species. So studies in the United States have shown we're spending about 87% of our time indoor. 87%, so the vast majority, including our children. Now, we're spending about 6% outdoor in vehicles, and then about only 7% actually outdoor, being fully exposed to the full spectrum at the natural sun. So there's quite a nice graph shown there about the percentage of time. So it shows a bit the importance of our glass, of the interlayers in the glass, the sort of control coating of the glass, because we're spending the vast majority indoors. Go to the next slide. This comes also to the spectrum, to the wavelength. This is a newborn baby. A lot of newborn babies have so-called jaundice. So their body or their liver is not able to kind of clean the blood properly. Now, a lot of these babies get into this kind of chambers and getting exposed to blue light, exactly about 460 nanometer wavelength. And then this light hits the body and the skin is able to then clean the blood. Yeah, and this is done for a couple of days until the liver can take over. It shows a bit how sensitive we are as human beings to certain light spectrum. Go to the next slide. We also know a lot of research nowadays, when research currently with guardian glass is focusing on, it's a blue light spectrum about 490 nanometer wavelength. And this is very important for the so-called circadian rhythm of the human being, which is the day-night rhythm. So people wake up in the morning, yeah, then people should get tired in the late afternoon. How does it work? So we need this blue light spectrum to get awake, yeah. And then we don't need this blue light spectrum if we want to fall asleep. This is why most of your mobile phones, your iPhones, Apple, Samsung, Android, whatever, there's this night mode. And when you switch on the night mode, this blue light spectrum is taken out because this blue light spectrum keeps us awake. However, if we don't have exposure to this blue light spectrum, we're not properly waking up and people are getting depressive. So is this blue light spectrum properly transmitted by our current solar control coatings, by the interlayers? Yeah. So this is currently a bit of research that is currently ongoing. If you go to the next slide, this shows very nicely what you need. We need the melatonin to fall asleep. So we need this during the night. But during the day, we need to have this cortisol. And this is clearly dictated by us. So our eyes perceive this wavelength of the blue light and then get this into our body. So it shows a bit how sensitive we are about certain spectrum of the light. And this is currently research where I'm currently focusing on. If you go to the next slide. This is one of the last slides. It shows the spectral transmittance of different coatings on our glass. And especially in the Middle East over here, we're using a lot of dark solar control coatings. So when people tell you, through the glass, we're getting natural daylight, it's no longer natural. It's a filtered light that we're getting in the Middle East with the pure purpose to reduce the solar heat gain. So all of our solar control coatings, they work in a way that will reflect or absorb the long-wave radiant heat, so the complete infrared spectrum. So the graphs on the left shows about the time. So we started with coated glass with so-called single silver coatings, solar control coatings. Then we came to the double silver and triple silver low coatings. So this is the evolution of the coatings. On the right-hand side, you see the kind of spectral transmittance. So we see the kind of wavelength, what is getting through the glass. Yeah. And while the early coatings, you can see at the top, they have a relatively homogeneous transmittance in the complete spectrum. Of course, I started filtering out the UV light, which also Kuraray is then going back to get it back in, for example, for greenhouses. But then we can see that the coatings are getting more and more solar selective, which means they're very selective in terms of what they transmit and what they reflect or absorb. And the modern solar control coating that we have nowadays, which at the bottom right, you can see they only transmit purely in the visible spectrum. Everything else is filtered out. Yeah. So our terms, natural daylight coming through glass, it's gone. It's no longer natural. It's a filtered spectrum. How does that affect us as a human being? We don't know. Nobody knows right now. So it's a bit of an experiment that we're currently doing with all of us. And also we as the facade engineers, as the facade professionals, do we know what this glass is doing? No one really knows. The problem is with the plants, it's quite simple because you expose the plants to light and it grows, but that's not grow. With human beings, it's a bit more complicated. If you go to the next slide, I think we are, oh yeah. So this brings me over to my, to Professor Dr. Lucio Blandini. I hope we can now swap to Teams.
Yeah,
Lucio is going to present about some latest research of the University of Stuttgart. I think we go to Teams.
this Teams correct here? Now, can you share this here? Okay, great.
So I hope you can see and hear me.
Yes, we can hear. I think you need to share your presentation
Yes.
so we can see your face, which is already a very good start. It's
Give me a second.
okay.
And I go to the presenter modus. Yeah. So
Okay, Lucio. So welcome, and the stage is yours.
thanks, Ben, for the introduction. I will talk about innovative facades for a sustainable architecture, and I will focus on one of our research topics, which is adaptive facades. So where is the motivation for approaching adaptive facade as a possible solution? I've been working on the praxis as a facade engineer for more than 15 years. And here, just one of the examples, the Etihad Museum in Dubai. I believe most of you may have visited it. And even if we were find a possible combination between high transparency and solar protection by carrying all the daylight analysis and using all the possible devices, using the proper coatings, proper fritting, and so on and so forth. It is just a compromise because we have to set up a glazing system which works in different conditions. And that was one of the main motivation then to focus our research work on facade where you can change properties over the time. And the location for our research work is the ILEC at the University of Stuttgart. 3 years ago, I've been succeeding to Werner Sobek as chair of this institute, which has been having done very famous chairs like Fraiotto or Jörg Schleich in the past. And the specificity of this place is that we focus on facades and structures, so it's a wide range, searching for lightweight solutions with a light ecological footprint. And we work together with architects and engineers, and this provides us a lot of different opportunities. So what you see on the right is our working space when it is all cleaned up like last week for a symposium. And so what are we working on? We set up within a so-called Collaborative Research Center, an interdisciplinary research group with among 14 institutes, mechanical engineers, structural engineers, architects, people working on chemical aspects, on informatic aspects, and so on and so forth, with the idea that if building would be much more dynamic, more capable to react to different conditions, that would lead to better performance and to less resources. So we've been inaugurating a tower, which is an experimental tower, 36-meter high. And the specificity of this tower is that we have not just a classical steel frame, but we have a steel frame with embedded motors, actors we call them. And this building is able just to move itself. And so as you can see then, when the actors are implemented, then the building can move up to 15 centimeters on the top. And the way we are now bringing and pushing him to move is the way we can dampen it down then in the future when there is a big earthquake, wind turbulences, and so on and so forth. So this is relevant for the structures, but today I'm focusing on the facades, even though a lot of the facade companies we are working together with are, of course, also interested in testing their IGU systems when they have to deal with such deflections. But this is a bit a different story. So today I'm focusing more on different systems. Here you see a liquid crystal facade systems we've been working on for a long time. Now we have a collaboration with the company Merck to have these kind of solutions on the top floor of the tower. So we have the chance at every floor to install different functions to showcase different solutions to have more dynamic facade systems. And by using proper hardware and proper software, we can react to completely different conditions. We can even track the position of the sun. And actually, it is even more potential behind that because we can combine the glasses, the smart glasses as they are, with the potential of artificial intelligence and create profiles, create solutions that are reacting much quicker than to the user. So we have a totally different interaction between people and architecture. So it's a different perspective that what Ben was talking about human-centric in terms of wavelength, but it place back the people in the center of the architecture and create a special relationship between people and facades. What we've been also working on is potential new solutions for solar shading system in combination with very light system, very light facade as ATFE. So we do not work only on glasses and IGUs, we work on different materials. And out of this folding mechanism, which has been developed by the NASA, and you can see some of the folding studies we've been doing together with people from the Aeronautical Institute, we've been developing a shading system which is supported by a cable nut embedded into an ETFE facade. So you see now that the 11th floor of the tower will have this kind of feature installed. And looking further, I mean, we have 12 floors, so there's a lot what we can do there, and we have already designed for, let me just go back. There is, exactly. So there is a textile system that we developed and patented, the so-called hydroskin, where we can collect water. I think you can now see the water flowing through this special textile system. And by doing that in the summer months, we can cool the atmosphere. It's through evaporation processes. Whenever it is a rainy day, we can use the same textile, of course, to collect the rainwater. This is more relevant in other regions eventually than in the Middle East, even though I've been experiencing that, especially in Kuwait, there is a lot happening then. And what you can see here is the measurements that we carried. So we can cool down 10 degrees by using this evaporation, and we can work adding this kind of special system on top of a classical IGU facade. On the ground floor, we are working with a very light fiber facade made of glass and basalt fibers, which can be open on the sides so that we have like a big theatrical curtain wall. And it is a different kind of adaptation, what we can show here. And but it shows the manifold of possible solution, how facades in the future can be more and more dynamic. And here you see some of the very special effects that are generated by the different fibers, and their pattern can be very, very free. It is regulated by parametric design and by computer fabrication. And so we can react to different need for solar shading. It is a solution we've been also using for the expo shades in Dubai and being further developed here for this experimental tower. And just to close up, one of the facade which is coming the next is, we call it shading skin. It's a special adaptive system for which is reacting on one side on the different solar inclination, and also reflecting the solar radiation then to the back to the sky in order to reduce data island effect. So this is something that will be installed in next year. And so you can see how this tower will be in the future populated by different systems, showing a different generation of architecture. I hope this provided a kind of overview of our research work. And if you have any question, Ben, I think there may be some space for that. Then I'm glad to address them. Thanks.
Okay, Lucio, so many thanks for the presentation. I think it was amazing. All of the presentations were, I'm really stand up and I learned a lot today. Now, I would like to ask all of the speakers to come to the stage and we would have a short Q&A session. So if there are any questions, please, the speakers, Pascal, come to the stage. Are there any questions from the audience? Of course, Lucio is online and is there anything you would like to know? Any questions? Anything was unclear? Andy.
Pascal, you mentioned a lifespan. I don't normally need one of these, but you mentioned a lifespan for laminated glass of 25 years. So one of the focuses, I think, as I've mentioned earlier, probably in discussions with people, is that in the Middle East we're getting to a point where all of the new shiny that we've been building since the 90s is now getting old and grey, a little bit like me, and we're going to have to start thinking about replacing a lot of this material. So double glazing units, obviously they typically start to fade and lose performance after 20 years or so. But laminated glass, even laminated glass that's been done well and is performing as expected to be performing, how long does that last? How long does a good, well-made piece of laminated glass? And can you maybe give me PVB, because I think PVB is more common.
The first laminate that we made was in 94, 95. Those laminates are still installed in Abu Dhabi, even in Saudi. So provided that we have visited, we had been called probably 5 years back for some replacements, but they were just few replacements of the total square meter that we have supplied. The changes, laminated glasses were predominantly used on the inner pane of the IGUs and more in the inside. So till now, it's been nearly 20 years. We do not see any issues with the laminated glasses. That's based on our experience since 95 when we supplied. We don't have issues. But here, definitely after, if it is external glazed laminated glasses, with the cleaning, with the moisture, with the sealant compatibility, we have seen that within 10 years or 15 years, you start getting haziness or delaminations. But internal glasses, I would say not an issue. I would say probably Kuraray would be best in a position to answer that. They have been 50 years in the industry. There are a lot of glasses laminated, internal laminated glasses. Even there are case studies of 35 years. No problems.
There's certainly from I suppose the biggest risk for any polymers, UV degradation. We know that PVB does not get affected by UV degradation, but other products do, like the gaskets, the sealants. And as soon as any moisture does get into the frame, then you have your risk. So providing, I think gaskets and sealants are a lot better now than they ever were before. And it's very much dependent on those. And going back to the other point you raised with regards to what do you do with all these units? You know, how do you recycle or downcycle or upcycle any of these? And I know that there's a lot of studies going on in Europe on the deconstruction of IGUs being able to separate the parts into its individual constituents. We're working very heavily with the likes of Arup and Callahan, looking for solutions to this method. We're trying, and internally we're doing a lot of testing on laminating glass. And for the last 40 years, we've been designing to try and keep it together. But now we're trying to separate it, which is a different thing. But I think sustainability is with us, whether we like it or not. And, you know, where you have this big call to replace units, we need to seriously look at how do we reuse or recycle those units. That's a really big question at the moment.
Thank you.
So are there any more questions? Yes, Prof.
Ben, this one's for you. So you mentioned the current coated glass. They are only the filter of sunlight, right? And not the complete natural spectrum of daylight. How soon can you get this stamped and authorized? I think you get a lot of glass refurbishment and all the facades of Dubai will have to be changed after that. You can set up more factories after that.
You know, we take it step by step. The first step is we have a draft German DIN standard. And this new German draft DIN standard, it will give us, besides the visible light transmittance, which is the kind of traditional way to measure the light transmittance, the so-called VLT, we're getting a new factor called melanopic transmittance of glass. So this will be a new factor that we currently pushing glass suppliers to add into their data sheets. So we're going to have, beside the shading coefficient, this sort of heat gain coefficient, reflectance. We're going to have the visible light transmittance, and the new factor will be the so-called melanopic light transmittance. Now, the difference between the visible light transmittance and the melanopic light transmittance is that we're putting a higher focus on the blue light spectrum that is important for the circadian rhythm of the human being. Different coatings behave in a different way in terms of transmittance of this certain spectrum. There's going to be mathematical functions to calculate that, and we already have the tools to do that. So I think it will be step by step implemented into the market. How bad our current glass is, it depends how much light you get through your glass. So if you have a high amount of lux levels, because you have a floor-to-ceiling glass, then of course you're getting a higher melanopic level or melanopic lux level in your rooms. If less glazing is of course less, so it's going to be a combination that we're going to look at the glass, but also the total lux levels in your room. Yeah. And if your lux level by itself is already higher, then also the melanopic level is going to be higher. So it's a bit of, I think it will start with the glass and then continue with the interior design in terms of looking at the light levels or the lux levels in your room and the depth of the rooms. So we're not there yet, but step by step we're going to get there. Yes. Thank you. I think there.
Yeah, we've been doing studies also in this area, and we have two products that fit within this. We have a natural UV interlayer, both in century glass and also in PVB, and this is ideal for increasing UV levels within the buildings that then can be, filtered further with coatings of sorts. But there have been very close links and studies, not just with plant life, but also with sampling building syndrome, which is very common. We're stuck in offices with artificial lighting, and in fact, to further add to your studies. Because of COVID and people being locked in their own environments, but they could actually control their own environment, and work productivity increased. But when people go back into their offices where they're unable to control their environment, their lighting and everything else like that, work was back to how it was. So we have the natural UV, and we also have an extra protect UV, which is used a lot in museums and places where you don't want UV degradation. So yeah, we're very much aware of the studies. I'd like to do a little bit more with you.
The question there.
Sorry, Ben. I still have I'm sat next to 3 years.
You're going to come up.
Yeah. It's just a quick and awfully simple question with a straightforward answer. It relates to exposed edges in laminated glass structures like balustrades and glass fins. There are always a couple of ways to think about it. Do you protect the edge or don't you? Do you leave the edges exposed or do you put some sort of cap over it? If you do, what you're sticking with. I've seen issues with both solutions. I just would like to know, Kuraray, what would you recommend in that instance and why?
Well, I think it's quite simple. We're lucky we have a solution. If you don't have a solution, then you'll be promoted to cap it, right? But if you have centric glass and you have open edges, it's not a problem. We've been manufacturing centric glass for many centuries, and we have open exposed edge samples in Florida, in front of the sun, on the coastal region, and those tests are still in operation 30 years later with no experience of any delamination. I think if you go with standard PVB, then you run that risk of hygroscopic ingress. We do have another product, the Ultra Clear, which is a higher adhesion standard PVB, but it's very different. It's ultra clear and very unique. That also has the same qualities, but certainly in the Middle East where you have the high heat, you need something a little bit stronger than the standard PVB for those sorts of applications.
Great, that's a good question. Okay, I think we're going to have the last question for today's session. I think we're all more or less hungry. We're going to have finger food outside. Because we're going to have some closing remarks by Allan later on, but let's come to the last question.
Well, actually, I wanted to ask something related to the light that you were discussing and the shading. We are in an era where the green buildings are being very popular. Everything is going environmental friendly. So I believe that the skin of the building is the major, let me say, component in this. So whenever you were talking about the filtered light that would go in and the lamination that can play a big role in it, does it consider as well on UAE level, istidama requirement, like the PER rating, whatever you value we are talking about? Are there any conflict between the light that is beneficial for the human being to be entered in a building and the istidama requirement and the green buildings?
It's a very good question. I mean, in the end, what we're currently looking at is that we are opening our solar control coatings to have a higher transmittance in a certain wavelength. This also means that it's, to a certain extent, it slightly contradicts to the green building design, because we will have a higher transmittance. So it's a bit of, looking at the sum of these two things. I think right now, all of the glass suppliers, like the big names like Nart and Sagoba, everybody was focusing on getting the shading coefficient down by having a maximum transmittance in the visible spectrum. Now, if we say we want to have a higher transmittance in a certain other wavelength, it's a slight contradiction. We see it as a new kind of so-called human-centric design. But you're absolutely right. I think currently we're just at the starting point. It's going to be a collaboration between medical scientists, between psychologists. I think just we mentioned about the UV light. I mean, for decades, we wanted to block out the UV light because it's causing color fading in shop fronts. People are saying getting cancer or kind of skin cancer because of UV light. But just recently, medical studies have shown that the UV light is quite important for human beings. So we were not aware of that. How much UV light do we need? How much blue light do we need in terms of lux? It's going to be all a bit unclear. So I think we're just starting to get into this whole thing. It's going to be very close collaboration between glass people, facade engineers, psychologists, medical, because a human being is not as easy as a plant. So the plant will grow and not grow, but with human beings, it takes a bit more time to show the effects. So it's a good question, but unfortunately, we are not there yet. But maybe in a few years' time, we're going to stand here again and we have the answer, hopefully. Okay, great. So we're going to give the closing remarks to Allan from Kuraray.
Thank you very much. Thank you for all the speakers and thank you yourselves. It's been great. It's been a lot of time in the making, a lot of organisation. I'd like to thank everybody involved and also the hotel for putting on a really great venue as well. Shane Dun Roadworks. There is food outside and there's soft drinks as well. Please do help yourself. There will be hot finger food being offered around. And obviously spread the word about the SFE because I think they've organised a great event this evening. And hopefully we'll see you all again very soon. Thank you very much.
He's finished now, isn't he? Yeah, so he's gone.